Welcome to the Everything Building Envelope podcast. On this show, we discuss topics relating to the exterior building envelope, such as waterproofing, glazing, cladding, roofing, and more. You can subscribe to this podcast on iTunes and Stitcher. For previous episodes, show notes, and bonus video content, check out our website, everythingbuildingenvelope.com.
Welcome, everyone, to our Everything Building Envelope podcast. I'm Chris Matthews, President and Principal for GCI Consultants, and I'm your host today. I'm really excited about our guests today. We have multiple guests from FIU, professors who will be talking to us about the wall of wind and other research projects that they do there on exterior building performance during hurricanes. So we've got Ioannis, Amal, and SJ, and I'll let you guys introduce yourselves and tell us a little bit about what you do at FIU, and I'm looking forward to our conversation.
Great, thank you. It's Ioannis Zisis from FIU. I'm an associate professor in the Department of Civil and Environmental Engineering, and I'm also the co-director of the Laboratory for Wind Engineering Research, which is part of the Extreme Events Institute, also at FIU. Amal?
Hi, this is Amal El-Awadi. Thank you again for the invitation. I'm assistant professor in the Civil Engineering Department at FIU. I'm also a member of the Wall of Wind team and the Extreme Event Institute. And my area of research and teaching is related to wind and the structure interactions in general. And SJ, thank you.
This is Sinja Lee. Typically go by SJ. First of all, thank you for your invitation. So I'm currently associate professor in the same department, Civil and Environmental Engineering at FIU, and I researcher at the Wall of Wind testing facility at FIU, and also NSF with IUCRC Center with Ioannis and Amal. I studied at the University of Illinois at Urbana-Champaign and moved to Miami in 2014. And I mostly work on the numerical modeling in various areas in civil engineering, including structural engineering and geomechanics. So before coming to US, I briefly worked at LG Chemical in Korea. I'm not sure if you know about that company. As a facade research engineer. Now I think they changed the name to LG Houses. So then I learned a lot about the details, how the facade is designed, tested, manufactured, and installed. So here at FIU, I'm currently working on a facade project with Amal and Dr. Chaudhary. He's not present here today, but he's the director of the Wall of Wind engine, the testing facility. So I look forward to talking about those projects more in this podcast soon. So I hope this is enough for my introduction. Thank you.
Great. Well, thank you all for agreeing to talk to us today. I think if you know a little bit about what we do, we at GCI are out inspecting buildings all the time for the effects of actual hurricanes on those buildings. So I'm super excited to talk to you guys today and learn more about the research work you're doing. So, Ioannis, can you just give us a little general background on the Wall of Wind, what some of the work you guys do there, and why it's important to the industry?
Absolutely. So our program, the Wind Engineering program, I think is a legacy of Hurricane Andrew. At FIU, we started with International Hurricane Research Center, IHRC, following that tragic event 20 plus years ago. One of the laboratories under the National Hurricane Research Center is the Wind Engineering group. We went through different iterations of the facility. At the very beginning, there were a portable system with 2 fans back in 2005, if I'm not mistaken. That was very challenging, but very interesting also. We carried out some research using that portable system, gasoline engines, and very loud,
Right.
but very useful also. And then that got us excited. We also managed to secure some more funding, and we upgraded the system to a 6-fan system, which was much more capable, obviously. We could test larger specimens and go higher in terms of wind speed. Finally, precisely 20 years from 1992, when Hurricane Andrew happened, we inaugurated the current version of the wall of wind, the 12-fan system. Major upgrade there. We have 12 fans, electric system, so 700 horsepower each. Were capable to generate up to 157 miles per hour wind speeds, which is approximately equivalent to a Hurricane 5 category. We have a flow management system to kind of like treat the flow before it reaches the turntable, the specimens, the models that we test. So we try to scientifically simulate the flow field, what we call the atmospheric boundary layer. The unique advantage of the wall of wind is obviously the size. It's the largest academic-based facility, like a large wind tunnel, if you may. So right. we can do testing at different scales, starting from a small scale that you see in a typical wind tunnel, 1 to 200, 1 to 100, but we can go up to full scale, 1 to 1. We can test like smaller structures or building components at full scale. And we can also do that at high Reynolds number. This is another scientific term, but it's very important. So we can go up to, as I said, 157 miles per hour at full scale, which is very important. On top of that, we can introduce wind-driven rain into the flow. We have some sprinklers on the front of the fans, and we can scientifically do that and study the wind-driven rain impact on the models that we test. So again, we have the 12 fans. There is a building that houses the wall of wind. We have a staging area where we can prepare for the test. That's where we use, the instrument, the models, and then we move them to the turntable to test them. We can do also destructive testing. That's another major advantage. It's an open jet facility. So we remove all the instrumentation, obviously. We don't want to damage the instruments. And we can go up to maximum wind speed and see how the different models perform, the full scale, as I said, like structure, and see what is the impact of this extreme wind on different buildings or different building components. At the moment, we have projects that are funded by federal grants, by state agencies, and also private industry. And let's not forget that this is FIU, Florida International University, so our focus is also educating our students. And wall of wind plays a major role in that. We have different courses in wind engineering, and both our undergraduate and graduate students are exposed to this research. We bring them to the lab and show them the type of work that we do. We're always like, current with, what is happening, and they know not only from a research perspective, but also practical perspective, what wind engineering is about, how the work that we do in the lab ends up in the building code or the wind standard, the ESC standard. So this is very beneficial for our students as well. And I guess as a closing statement on this, in your question, with the research we do at the wall of wind, we try to quantify and communicate the hurricane risks and losses. And at the same time, we want also to mitigate the impact. So we do a lot of research related to mitigation. And obviously, sustainability is another big word or theme, research theme in our research agenda. And that applies, all these different themes apply on different types of residential buildings, commercial buildings, infrastructure, power lines, all different kind of things.
So a lot of what we do involves water leakage and wind damage, kind of the combination of that, as you guys are doing with when you're introducing water into your testing. I was curious, can you give us an example of that someone who's not a professor like me could understand? Yep. Are you introducing the water before there's damage from the wind, as the wind is damaged? How does the water play into some of your investigations of the wind effect?
Yeah, that's a very good question. We do both, actually. So wind comes with rain, obviously, and that's what we do in the lab. That's what we try to simulate. So when we turn on the fans, and if it is a wind-driven rain type of project, we're going to introduce also the rain component into the flow. Now, how do we carry out the test? Depends on the application. So I can talk about one of my projects, and I guess Amal and SJ will talk a lot more about the facade project that they did recently. But I think I completed that project about like 2 years ago. It was collaboration between FIU and Florida Tech, colleague that we have there, Jean-Paul Pinelli, Professor Pinelli, and our focus was interior damage. So specific to your question, in this case, we simulated the damage ahead of time or different damage scenarios on low-rise buildings, the typical low-rise residential structure, and we assume that we have a broken window or a portion of the roof is missing. And then we introduced the rain component, and we wanted to see how the water is distributed on the interior compartments of our model. We had different roofs. So depending on the damage scenario or the damage level, we could quantify the level of damage on the interior of the building due to water intrusion. So that was one example. In other cases, we do like the model is intact. So we have a strong wind, damage might happen. We add the water component and see what happens, and it could be like related to, I don't know, like shutters, or it could be like sliding doors. We have done some projects, or roofing element. And we want to see how much water goes inside the house during a strong wind event and after the damage is initiated.
Okay, interesting. Yes. So we're kind of doing that on a very rudimentary scale in the field when we were investigating some of these buildings that have been affected by wind, and we're water testing afterward, because lots of times we get reports from the building occupants that something that wasn't leaking prior to the storm and doesn't exhibit a lot of visible evidence of damage is now leaking during regular thunderstorms, that kind of thing.
Yes.
So
yeah, we got similar feedback from different partners, industry partners, I would say. And that is basically the reason we started doing research in that field. And Amal and SJ, they did that project, and they're going to have a lot more to share, I guess.
Okay. All right. Well, and maybe that leads us right into the project that you guys worked on, Amal and SJ. Can you tell us some about that?
Yeah, thank you, Ioannis, for the great introduction. I think it will make my talk easier. So basically, this project was funded by Web Center, IUCSC Web Center, which is a collaboration between industry, NSF, National Science Foundation, and academic institutions. FIU and Texas Tech and FIT are part of the center. So we have a site at FIU, basically. So the industry partners were interested to see how the facade is, like certain types of curtain wall systems, are behaving against wind and wind-driven rain. The interests are coming from industry, like manufacturer, like Thermostalisa, and also insurance companies, because they wanted to see like the projections of like insurance claims, for example, after hurricanes or water intrusion. Sometimes it's all about water intrusion, not the damage of the facade itself. So there was like a high interest in that project from our industry partners, and we worked with the manufacturer in the group, which is Thermostalisa, to design like a full-scale specimen representing two types of facade. They provided us with a single scan facade and a double scan facade system. Thanks to the large section of the wall of wind, we were able to test a full-scale model. So we didn't reduce the specimen or scale it down at any point. We used like a full-scale model of the specimen. We created like a small room from that facade system. The dimensions, SJ, you can correct me if I'm wrong, it was like around 16 by 8 feet length and width, with about like 12 feet height.
Yeah, so 12, 10, 6, you're right.
Yeah, 12, 10, okay. And we used a single scan facade. We tested two different configurations, one representing like a smooth facade with no protrusion elements. And the other one, we wanted to mimic like the case where we have like a shading devices, which the industry use or for architectural reasons.
Sunshades on the exterior of the curtain wall?
No, we were collaborating. Like I was taking care of the experimental part, and SJ was taking care of the numerical simulation. So basically, there was two methods used in that project. We wanted to test the specimen experimentally and then try to simulate the same experiment in like using numerical simulations. and then we can extend that to like a parametric study. I will let SJ talk more about the numerical form. So I was just trying to give an overview of the experiment. So for the single scan facade, we, as I said, we tested a smooth surface, and another surface was vertical fins or vertical shading device to see how the main objective basically was how the addition of that fin is important from aesthetic point of view and architectural point of view, but how it would impact the performance of the structure. How the vibration would be different, and is there any correlation between wind-induced vibrations and water intrusion? So we applied wind-driven rain, like what Ioannis was mentioning, to see a different wind speed, different wind directions, to see how they are correlated, both wind-induced vibration and wind-driven rain for both cases, like the flat surface and the surface with shading device. SJ? You want to talk a bit about the initial form?
Right. So thank you, Amal. So I'm collaborating with Amal on this project. So definitely the framework we like to develop is kind of integrated experimental and numerical analysis framework for the facade system. So definitely our objective, one of the objectives would be to inform design standard for curtain or facade industry. Regarding that the wind-induced resonant vibration of the facade system. So ASC 7 standard says the structures with natural frequencies above 1 Hz do not need to be analyzed for wind-induced dynamic effects. So this criterion was originally developed with the typical building size in mind, but this has been often viewed by some practitioners as also applicable to building facades and which are much smaller and stiffer. So it was reported that many facades failed because of the wind-induced resonant vibrations, and definitely their natural frequencies are clearly above 1 Hz because it's smaller and stiffer. So building facade, so the 1 Hz criterion can be clearly misleading. So what we are doing is Amal is responsible for the experiment testing at the wall of wind, and we use that experiment data to calibrate the numerical model we developed using finite element method. So we cannot model, finite element method, every continuous system is discretized into a smaller so-called finite elements. And then we just mathematically model that system into a set of the linear equation and solve that in computer. And the beauty of this approach is we can do some parametric studies without any further experiment at the wall of wind. So we calibrate the model based on the acceleration and strain data we obtained at the wall of wind. And then we just make the system to be calibrated based on data such that it can perform as shown, as observed it at the wall of wind experiment facility. And then we just do some kind of parametric studies like different wind direction, different wind speed, and also we just change some properties by change the size of the frames, and also change the thickness of glass, and also change the properties of the silicon glazing, and so on and so forth. And then we can study the wind-induced vibration of the different systems in the computer by changing those parameters. So that is the beauty of this approach. So we definitely want to investigate the interrelation between the wind-induced resonant vibration and the water intrusion, because water intrusion is actually the real problem in many cases, so that the damage is interior and utility inside the building. So definitely the wind-induced vibration with more wind-induced vibration, and there it is likely to have more water intrusion inside the building. So we try to better understand the correlation between these two phenomena. So that is definitely one thing. And also I work with Dr. Chaudhary. So this is kind of related project, but we also use the same specimen with focus on the upper part in the facade system. So often, the facade system has the upper part like window,
right?
Even for the curtain wall. But the main thing here is often that the upper parts just fail because of fatigue in the hardware. So that is caused by often different natural frequencies between the upper parts and the main facade. So that is affecting the hardware, and that causes a fatigue failure. So we also try to look at failure mechanism through this kind of integrated experimental and numerical analysis framework.
And you assess that further through your modeling program, or did you actually test different hardware in the wall of wind, or was that more through the modeling program?
So we first need to do the testing. So we already tested, and then we saw the behavior, dynamic behavior of the operable parts. We put the sensors, the accelerometers, and the strain gauges, and then we got the data, and then we calibrate our numerical model with operable parts so that it can behave the same as we observed in the experiment facility based on the acceleration and the strain gauge, and then we can better understand the mechanism of the failure. So we indeed saw some different frequencies between natural frequencies of the operable part and the main facade system, and we believe that is somehow affecting the failure mechanism, the fatigue failure mechanism of the hardware.
Interesting. As I had mentioned, we're out looking at these failures in the real world after the hurricane, and I don't think that concept has even been considered at the point in the process that we are, because all the discussion is buffeting winds, opening joint, those kinds of things, but it's not this vibration component that you're investigating.
Yeah, vibration is a big issue. Yeah, definitely. And so we are seeing some limited number of research in this topic, and hopefully we can contribute to the body of knowledge.
Great. Well, and as you said, ultimately from the industry standpoint, it's the mitigation factors, right? Once you guys understand better how to make these systems perform better, then we in the industry can respond to that and design accordingly.
Sure. Yeah, definitely. In academia, we first start with understanding, characterization, and then mitigation will be followed for sure. Yes.
Right.
Sorry, Amal. I think you wanted to say something.
No, I was seconding like your comments. Yeah, having an industry partner in that project, collaborating with us, helping us with the installation and specimen design was it was essential actually, because we didn't want to change anything that happens in reality, in the real life, like there in the site, from what we are testing. So we wanted to be like very accurate, replicating like a real case scenario and test, so we can really inform like a meaningful result. So it was also very important to have industry experience helping us to advance this knowledge actually.
Yes. Well, and it sounds to me from your description of your test specimens that they were similar to what we would test for certification of windows, doors, curtain walls, etc., for both the impact resistance, water resistance, and structural.
Yeah.
Go ahead. Sorry.
Oh, sorry for interruption. Yeah. This is interesting part, because we wanted to test like in a proper way, but it's not replicating the certification testing. So basically, we have some questions about like the how the certification testing is realistic, to assess like the wind-induced vibration or wind-driven rain performance of a facade. Because currently, like for example, the static pressure testing, that is not representing a real dynamic wind effect on the facade, right?
Right.
Having like just one fan focused on one panel is not replicating the case. So we have some certain questions related to the certification testing, and we wanted to assess that in the lab by measuring or by trying to replicate a real case or a real life scenario, basically, for wind and rain together. So for wind, for example, we tested wind speed from 90 miles per hour all the way up to 140 miles per hour. For rain as well, we wanted to simulate a wind-driven rain case scenario that happens during hurricane events. So by matching like real rain events that were reported in literature. So how is that close to certificate? This is a whole new question, or another question that we are trying to answer in that project as well.
Right. And I think that could have a big impact as well moving forward in the industry if the certification testing was more representative of real conditions. not just a static pressure test, as you mentioned, these specific laboratory tests, which maybe don't really replicate what these systems are exposed to, at least in the areas we're talking about, coastal regions where there's hurricanes, those kinds of things. And we talk about that a lot when we're consulting with architects, designers, in that here's what the code requires, here's the certification of these systems, what they meet, but you're building this condominium on the beach where a hurricane will come. It's just a matter of when. And do you want to design it to a higher standard so you get better performance, which would go all the way back to the certification testing if we were really doing it the right way? So that would be great feedback. I'm sure it'll take a long time, but if your research came back all the way to the industry and we looked at it from the certification standpoint, I think we get a lot better performance in our buildings moving forward.
Yeah, we hope to get feedback from our industry partners and interested parties, policymakers. I'm sure that will take time, but I think that was like a first step.
Yep. And you mentioned Permis de Lisa was your system provider for your testing, and we've worked with them specifically on building real project in Miami Beach, that kind of thing, big condominium projects with their systems. So they're a great partner and representative of what's being built right now.
Oh, that's interesting to know. Yeah. They were a great partner in that project. Yeah.
Well, I thank you guys so much for joining us today. I think I got most of what you were explaining. Some of it's over my head, but it's super interesting, and we really appreciate your joining us in our podcast. I think our listeners are going to get a lot from the conversation. Any closing remarks that any of you have that you'd like to finish up with?
Thank you for providing us with the opportunity, to discuss and present what we do at the Wall of Wind. I should mention that, again, Wall of Wind is part of an academic institution, FIU, so the focus is educating the students, but at the same time, we try to stay close to the industry and to listen to the problems they have. And I guess the discussion we had today is a great example of how things started, doing research for a real problem, and staying connected to the industry. That always helps us be relevant. The research we do is a practical application, a problem that exists out there, and we try to investigate that in the lab. So again, thank you for the time you gave us today to discuss all these things.
Yeah, and I can definitely attest to the fact that it's a real problem because we're out looking at buildings every day that could have performed much better, even when there's not catastrophic damage. So I think the work you guys are doing is right on track with what is needed moving forward. So thank you again for joining us today. We invite all of our listeners to investigate our services more on www.gciconsultants.com. I thank our guests from FIU, and I look forward to talking with you again on our next Everything Building Envelope podcast.
Thanks for joining us today. Please subscribe to this podcast on iTunes or Stitcher. For more information on the Everything Building Envelope, previous episodes, show notes, bonus video content, and much more, check out our website, everythingbuildingenvelope.com.